Thank you very much for your time today. Hope everyone is doing well and keeping safe. Today's webinar is split into two sections. The first section, that would last 30 minutes, focuses on presenting the technical details of the process. During this session, please feel free to send us your questions through chat. This session will not be interactive in the interest of keeping the entire webinar within 45 minutes. During the second session, that would last 15 minutes, we will try to respond to all your questions. This session will be very interactive. Now, look at the pretty components on the screen. They are all made of steel or stainless material, and they are produced in high volumes, tens to thousands to millions per year. What if we asked you to produce them in a CNC machine shop? Impossible, right? Don't worry, we have Mr. MIM to your help. With the MIM process, you can produce thousands of parts per day without even getting near a metal cutting machine. Let's understand what this wonder process is. Do you remember conventional powder metal process? It's also called press and sinter. In this process, we take metal powders, press them with high pressure in a die using top and bottom punches, add some core pins to produce holes, etc. The pressed parts are sintered in a furnace to get to 90% of the material density. Great process, but not good enough, because the process can produce only two-dimensional shapes and poor material properties because of low density. Now, you also know plastic injection molding process. Who doesn't? Injection molding process allows you to produce complex three-dimensional shapes. But this process can deal with plastic and low-melting materials like zinc and aluminum. Wait a minute. How about injection molding of the metal powders instead of just pressing? You can't? No. Yes, you can. Just mix the powder with a little plastic binder. The mix flows like semi-solid material under heat and pressure. So, let's ask powder metal and injection molding to marry each other and see what happens. And they said yes. Metal injection molding was essentially a marriage between two existing processes, powder metal and plastic injection molding. The marriage happened around the mid-80s. Sorry, we weren't around. But here we are now to take the benefits of that marriage. That's all that matters. Metal injection molding is a simple four-step process. Step 1. Mix the metal powders with some binder, usually a mix of polymers and wax. Mixing is done under heat so that the binder material melts and coats each metal particle. This produces a homogeneous mix. The mix is converted into small pellets for easy storage and transfer. At this stage, the mix is called MIM feedstock. Producing MIM feedstock is a highly specialized process. Most of the MIM companies buy ready-to-mold feedstock from a third party. We, at IndoMIM, produce our own feedstock in-house. Producing feedstock in-house provides a lot of cost advantage, and we can monitor the quality better. Step 2. The feedstock is injection molded into complex shapes using plastic injection molding machines. During the injection molding process, the MIM feedstock is heated just enough to melt the plastic. So essentially, we inject semi-solid material into a custom-made mold. A molded shape is only a consolidation of the metal powder with the help of plastic. At this stage, the parts are called green parts. The green parts should be handled delicately to avoid damage. Step 3 is to remove part of the binders. The process is called debinding. After this process, the components are called brown parts. The last step is to sinter the brown parts and remove all the binders added. During sintering, the high temperatures enable the metal particles to diffuse with each other to get to 97% minimum density. After the sintering, the components are 100% metal with no binder material in them. Hence, they display very similar material properties as corresponding wrought material. So, we made complex shaped metal parts without even getting anywhere near a metal cutting machine. Still don't believe it? Let us watch a video of the process. This short video was shot at our plant in Bangalore, India.
The MIM process begins with compounding, manufacturing fine metal powder which blend with thermoplastic and wax binders in proportional amount to make the feedstock. The feedstock is injected in the metal mold to form the net shape at molding. After this process, the solvent extraction process is used for removal of primary binders at the debinding process. The last stage occurs in batch vacuum furnaces or continuous furnaces, to remove secondary binders and densify the component, which is coined as sintering. After sintering, MIM goes for required heat treatment and special process to enhance the material properties. The final products go through standard checks for quality assurances before being delivered to the customers.
What started as a science project in the 80s has grown into a $3 billion global industry and growing at 20%. Applications of metal injection molding are found in almost every known industry: automotive, consumer products, firearm and sporting goods, medical devices, and electronics are some of the broad categories of the global market. If you have small intricate steel or stainless steel components, MIM will be your preferred process. Automotive companies like Garrett, BorgWarner, Mitsubishi, Bosch, ZF, Cummins, Caterpillar, etc. use a large number of MIM components in their assemblies. The Lightning connector on your iPhone is a MIM component. Apple alone consumes $600 million worth of MIM components in a year. If you owned a handgun made in the USA, you probably have seen several MIM components on it. A typical handgun has 15 MIM components in it. Pretty much every mass-produced endoscopic or laparoscopic surgical device has MIM components in it. Indomim alone developed 6,500 plus varieties of MIM applications in the last 2 decades. We service 350 plus customers globally. Okay, looks like you're on board now. Now let's discuss the nuts and bolts of the process in more detail. Step 1 is mixing the metal powder with binders. This step is called compounding. Metal powders are normally produced through gas atomizing. Gas atomization process produces spherical-shaped particles. Round-shaped particles flow better during the molding process. Typically, MIM powder particles are less than 20 microns, significantly smaller than metal powders used for conventional press and sinter process. The powder contains particles between 3 microns to 20 microns in precisely maintained particle size distributions. This is extremely critical to achieve the best possible powder packing in a molded component. Metal powders can be an element mix of various alloying elements or pre-alloyed depending on the final chemistry required. Most of the stainless steel and nickel superalloys are pre-alloyed. MIM powders are expensive to produce because of the small particle size tight controls on particle size distribution. They cost between $10 to $75 per kilogram, depending upon the alloy content. Most of the MIM powder producers are located in Europe, Japan, and China. MIM powder costs are among the main cost drivers in a MIM component. Hence, larger size components don't make good MIM candidates. Normally, components less than 100 grams are economically viable through the MIM process. At Indomim, we find 0.20 to 30 grams weight range, the sweet spot. Binders. The binders are normally a mix of commonly available polymers and wax. Most of the MIM companies in the world use a wax polymer recipe for feedstock. The actual recipe is commonly considered as proprietary information. As the metal powders are completely covered with the polymers during the mixing process, the MIM feedstock has a very long shelf life. MIM process offers a wide variety of engineering steel, stainless steel, and industrial ceramics. Indomim offers 80-plus material options, significantly larger than our nearest competition. Our in-house R&D material development team continues to add to the list on a regular basis. As you see, for every engineering application, there is a MIM material option. However, please remember that any metal that melts below 1000 degrees Celsius or 1832 degrees Fahrenheit cannot be processed through MIM easily. Hence, you may not find a MIM company that would deal with metals like aluminum, zinc, copper, etc. Step 2 is injection molding of the feedstock. This process is very similar to plastic injection molding. As a matter of fact, we use the same machines used for plastic injection molding. However, there are some differences. The molding temperatures are just enough to melt the binders added. So, essentially, we are injection molding a semi-solid material. Hence, MIM molding requires much higher pressure. This means MIM molding machines are usually oversized. Also, given that the metal powders are abrasive, the screw and barrels are made of special material. During the molding cycle, the molds are both heated and cooled. The injection pressures, injection speed, and a host of other molding parameters are monitored using a closed-loop system. Hence, MIM molding machines are usually CNC controlled. The molded parts, now called green parts, are normally picked by the robots and placed on ceramic trays. Remember, at this stage, they are just metal powder held together by the plastic binders. They have to be handled delicately to avoid any damages. The runners are normally reground and reused after mixing them with the virgin feedstock. We will discuss more about this in the subsequent slides. Now, let's talk about the molds. The molds are made with the usual tool steels, commonly used for plastic injection molding. However, as the MIM feedstock is abrasive, the mold life is usually smaller than plastic molding. We guarantee 300,000 shots mold life before replacement is needed. So, a 4-cavity mold can produce 1.20 million parts during its lifetime. This is still a significant tool life for most of the programs. MIM molds are normally oversized to accommodate the shrinkage during sintering. The shrinkage on the material depends on the binder recipe used. Normally, a MIM mold made to suit a feedstock recipe cannot be used for another MIM feedstock recipe. This makes it difficult to transfer a mold from one MIM vendor to another, as they rarely follow the same binder recipe. The number of cavities on the mold depends on the size and complexity of the part. 2 to 4 cavities are common. However, MIM molds with 16 cavities are also used. Indo-MIM has the world's largest MIM tool room that can produce 70 molds per month. This allows us to offer the shortest development lead time in the industry. Our development lead times are 6 to 12 weeks depending on the complexity of the program. Our mold development costs, including process validation, are usually between $15,000 and $50,000 based on the complexity of the program. We also offer prototyping services for the applications when customers are not sure if the MIM option works. Normally, a proto tool with 30 samples would cost you between $10,000 and $18,000. Lead time for proto samples would be 3 to 6 weeks. Moving on to step 3. Once the feedstock is molded into shape, we don't need the plastic binders on the parts. The process of partially removing the binders is called debinding. The MIM binders are broadly categorized into 2 categories, primary and secondary binders. At debinding stage, we remove the primary binders through a solvent extraction method. Debinding technique depends on the binder recipe used. Some MIM vendors use catalytic debinding and some use thermal process. Solvent-based process is the most economical and efficient method. As you can see, the green stuff inside the green part is all gone after debinding. The part at this stage is called brown part. The weight loss on the components is closely monitored during the debinding process. The entire process is done in an automated closed-loop system. The solvent used in the extraction process is regenerated. Debinding cycle times depend on the wall thickness of the parts. Thick-walled components take longer to debind. Components with wall thickness greater than 6 millimeters are difficult to debind. During debinding process, we achieve 2 important things. 1, we remove the primary binders from the components. 2, we created a fine network of interconnected porosity in the component, which helps us to remove the secondary binder during sintering process, the last stage in the MIM process. All the space occupied by the primary binder is now a network of porosity. Sintering is the last stage. Brown parts are now moved to sintering ovens. Sintering furnaces can be batch type or continuous type. Batch sintering furnaces are usually vacuum furnaces with nitrogen, argon, or hydrogen cover gas. Continuous furnaces use combination of nitrogen and hydrogen gases as the cover gas. Sintering temperatures depend on the material, usually range between 2,300 degrees Fahrenheit and 2,500 degrees Fahrenheit. Sintering cycles are between 25 and 35 hours long. The first 12 hours of the cycle are spent on removing the secondary binders through thermal debinding process. After all the binders are removed, the furnace temperature is ramped up rapidly to the soaking temperature where the metal particles diffuse with each other. At the end of the sintering process, all the particle boundaries are replaced by grain boundaries. At this stage, the component shrinks by a specific percentage, squeezing out all the empty space left behind by the binders. The shrinkage is mostly isotropic, meaning the component shrinks at the same percentage in all the directions. As you see, there is a significant size difference between a green part and a sintered part. The component shown is made of stainless steel 17-4pH, which has 16% shrinkage. Shrinkage percentage at the sintering stage varies by 1% total. This variation determines the dimensional tolerance achievable after sintering. Most of the MIM companies achieve dimensional tolerance on the components within plus or minus 0.5% of the feature size. With better process control and equipment, it is possible to achieve plus or minus 0.25% of the feature size. It is important that the parts rest on a flat surface during the sintering process to avoid sintering distortions. Part geometries that don't have a good flat surface to rest on will require special ceramic setters. Normally, ceramic setters add to the overall development costs. Indomim has in-house ceramic setter production capability that greatly helps lower cost and shorten development time. Post-sintering, MIM materials achieve minimum 97% density. After sintering, the components are 100% metal, all binders gone. The remnant's porosity in the material is not interconnected, hence, they don't influence the material properties in any significant way. As you can see, MIM materials achieve 95% of the corresponding wrought material properties. For most applications, this is acceptable. However, remember that MIM materials don't exhibit directional material properties. Sintered MIM components can be mechanically worked, heat-treated, machined, plated, and welded just like wrought materials. Pretty cool process, huh? Is this a miracle process or another snake oil? I would say neither. Like all other metal working processes, MIM has some limitations and some great advantages over other processes. MIM is a highly scalable process. We can address very low volumes, say less than 5,000 pieces per year, or we can address very high volumes, normally in several millions per year. The process can be easily automated to achieve very high productivity. Here are the scenarios where you may want to consider MIM process. You need a unique chemistry, and the material is not available in the market. You want to integrate a multi-piece assembly into a single piece. You want to convert a plastic or zinc molded part into steel or stainless steel because the current version does not have required material strength. You don't want to do complex machining on parts of high volume, especially if the material is hard to machine. When you want to design a component with MIM as the manufacturing method, you have almost 360-degree design freedom. You can add additional or difficult features to the part without adding cost to the component. You can add different textures, logo to the component surface. Produce internal and external threads. Remember, on the right application, MIM can save up to 80% of the component cost. Still not convinced? Just send us a print or CAD model or even a sketch on a napkin, and we will let you know if you can save money. Let's talk about the MIM design guidelines. MIM process closely follows plastic injection molding. Hence, all the mold design rules applicable for plastic injection molding are generally applicable. If the component can be injection molded in plastic, we can mold the same part using MIM material. It's as simple as that. Normally, products less than 50 grams and with footprint less than a maple leaf would be good candidates for the MIM process. However, the component should have enough complex geometry to compete with the conventional machining process. When you consider MIM as the production process for a component, be prepared to accept gate and ejector pin witness marks on the component. Large corner radius, uniform wall thickness are all considered as good design attributes. Draft angles, where possible, are good for molding. Minimum wall thickness should be 0.30 millimeters or 0.012 inches. Maximum wall thickness can be 8 millimeters or 0.30 inches. I would say the sweet spot is between 2 and 4 millimeters. Internal and external threads up to 6 millimeters in size or 0.25 inches can be easily molded. Pay attention to length to diameter ratio. Long parts with thin walls are normally not good MIM designs. MIM mold designs have come a long way in the last 20 years. Conformal cooled mold inserts that are used in plastic injection molding are also popular among the MIM tool builders. Now that you have accepted MIM, the question is, why EndoMIM? Several reasons, but the most important ones are quality. We have all the required industry-specific quality certification. With 2 of our production plants located in low labor cost regions, we are generally 30 to 50% cheaper on product cost compared to a MIM company located in the USA or Europe. Capacity. EndoMIM has the largest installed capacity in the MIM industry. Tooling. Our enormous in-house tool room can produce approximately 70 MIM molds per month. This enables us to achieve the shortest development lead time and lowest development costs. Material options. We offer 80+ material options, way more than any of our competition. Experience. We developed 6,500+ MIM applications for our 300+ global customers from all the market segments. All these experiences are made available to you. Finally, we are where you are. We have production plants in India and San Antonio, Texas, USA. Our sales offices and sales representative agencies are always at your call, and we can show up at your location within 24 hours notice. Our highly qualified engineers and sales professionals are available at your service round the clock, 365 days in a year. Finally, here are some pictures of MIM components. I'm sure some of you may even recognize the components. We will email the PDF copy of this presentation for your reference. Feel free to distribute it to your colleagues and friends. Today, we truly appreciate your time with us. Now, for the next 15 minutes, we are ready to take your questions.